in these chapters, we're going to be inventorying or looking at things regarding what's the motion of their center of mass. All right, because when a wheel rolls down, or when a car wheel goes by, if you look at a point on the rubber tire, okay, or where the lug nut is, okay, that's a much more complicated path than just looking at the exact center of the axis of rotation along the axle. Okay, so I want to look at the concept of rolling. All right, so let's look at a stationary wheel rotating with some angular speed. So let's say you take off your bike wheel, okay? You're holding it with your hand. Okay, there's your hand, all right? I'm gonna take the hand away. Okay, and I'm using this little symbol right there, okay? This symbol represents an axis of rotation. Okay, so I make a little triangle with a dot. That means this thing is rotating about that axis, all right? Okay, so this thing is just purely rotating. You're holding the axle and you gave this thing a spin and it's rotating. So I just drew the velocity at different points of the rim. So the top of the rim is headed to the right, that part's headed down, that's headed to the left, that part of the rim is headed up. Okay. Now we know previously that the linear speed of any part, okay, depends on how far you're out from the axis of rotation. So V is R omega. Okay, remember, every part of the wheel has the same omega, okay? Because remember, omega is delta theta per time. So if I take, we did this point before was A and that was B, okay? All right. Both point A and point B both go the same delta theta, right? 2 pi radians in the same time. Okay, so that's why there isn't an omega for A and omega for B. Okay, there's just one omega for the entire wheel. So this wheel is purely rotating, and I just drew the directions of the linear velocities v at different points of the wheel. Okay, now I'm going to take the same wheel and I'm going to have it roll along the ground without slipping. All right, and I'm going to show you a video in a second what's going on here. Okay, so this is just a bike wheel, and it's going to rotate with the same angular speed as in this picture. Okay, so let's say I gave this thing a spin with my hand, okay, and it's rotating around, and whatever the spin rate, I'm now going to roll it on the floor with the exact same spin rate. Okay, now I said up here it's going to roll without slipping. All right, so if you're in your car and you slam your foot on the gas pedal, okay, your tire is going to spin really fast, okay, and your car is not going to go very far, and then eventually the tire is going to slow down due to friction, and then it'll grip the road, and then it's going to start to move. All right, so I'll show you a video of a bowling ball that is thrown, and when it hits the ground, it's rotating really fast. Okay, it's slipping, and then it eventually grips, and then it starts to roll without slipping. Okay, so that's what it means to roll without slipping. Okay, and then I'm not going to keep saying the phrase without slipping. I'm just going to say something rolls. Okay, so if something's rolling, it means it's not slipping. Okay, so I have the wheel. Okay, so what it is I drew, here's the center of mass. Okay, so remember previously, if I make a little X with a circle, okay, that's the center of mass. There's my center of mass. All right, and this thing is moving to the right. And let's say the center of mass goes from that point on the road to that point on the road. Okay, so I'm not calling this the x-axis, I'm calling it the s-axis. Okay, now why am I using the letter s? Okay, we'll see. So this is the distance s that the center of mass moves. And there's some paint on the ground. All right, and as the tire rolls over the paint, okay, that paint, whoa, winds up along the edge of the tire, okay, along the rim of the tire. So this distance s is the same as that arc length s. Okay, and I said in geometry class and trig classes, they like to use s for arc length. So if that's an arc length s, I'm going to call the path along the road, S. That's why I call that the S-axis, okay? Okay, so the speed of the center of mass, okay, so remember speed, okay, speed is distance over time. So the speed of the center of mass, okay, speed of the center of mass is the distance, okay? I could have called it S, I just called it delta S, okay? So that's my distance, delta S, or S, divided by the time. Now, I'll just add that in the video, I used deltas. I did delta S over delta T, okay? And I used a delta over here, okay? But the velocity of the center of mass is ds dt, right? And arc length S is r theta. So when I did V is ds dt, right here where I have an S, I put in r theta, okay? R is constant, comes outside, and then d theta dt is the angular velocity omega. Okay, now we know from earlier, when we had a sector of a circle, that was arc length, and that was the radius, that was theta, that the arc length S is related to the radius and theta, like that. So S is r theta. So right here where I have an S, I put in r theta. Okay. Now the radius of the wheel is constant, so that comes outside. Okay, that's outside. And delta theta per time, that's the angular velocity omega. So that says V center of mass is r omega. And that's the condition for rolling. Okay, so the condition for rolling is that as long as the speed of the center of mass, right, is r omega, that means it's not slipping. Okay, so let me go back again. So here I have a wheel rotating with some angular speed omega. Okay, now I have that same wheel, okay, rolling with the same omega. Okay, and if that's happening, then that condition is met, that the speed of the center of mass is r omega. Okay, here I have V center of mass is r omega. If I divide up both sides by delta t, okay, velocity per time is acceleration, and on the right, omega per time is angular acceleration. So that's where this came from. Okay, so this condition for rolling, V center of mass is r omega, also says that the center of mass, or the acceleration center of mass, is r alpha. Okay, so we just had this wheel rotating with some angular speed omega. I took the exact same wheel and had it roll such that the speed, the rate that it rotates, omega, is the exact same as it was just purely rotating. Okay, and when that occurs, the speed of the center of mass, okay, is r omega. So the speed of the center of mass is r omega, is the exact same omega as this thing as it rotates. All right. So the center of mass, okay, has the same linear speed as the rim did when it was purely rotating. So when this thing rolls by, you're standing there, you're watching this thing rolls by, okay, the speed of the center of mass is the exact same speed that the rim had when you were just holding the wheel and rotating it. Okay, so what that says is if I have a wheel that's rolling, okay, like a bike wheel or a car wheel on a car, okay, every point on the outer rim is doing two things. Okay, every point on the outer rim has two motions on it, or two motions associated with it. Okay, so here's the two motions. Okay, so here I show the wheel rotating. So every point on the rim, okay, there's a rim, there's a point on the rim. Every point on the rim has linear speed r omega due to pure rotation. That was this picture. Every point on the rim has linear speed r omega because it's rotating. Okay, so I drew that here. Okay, this is the same picture as that one. Okay, here I didn't draw it over here and here, so I'm just drawing it at the top and bottom. I could have drawn it anywhere, but I just drew it at the top and bottom. Okay, so every point on the rim has linear speed r omega because it's purely rotating. Okay, but okay, so that's there and there. But the wheel is attached to the car, which is headed down the road. Okay, so not only is every point on the rim have linear speed r omega due to rotation, okay, but number two, every point on the wheel, okay, and the rim is translating to the right with the same speed as the center of mass and the rest of the car. like that. Okay, so for example, here's my car, headed to the right. Okay, so that's the speed of the car, right? So every part of the car, okay, is moving to the right with the same speed as the door handle, as the person, okay, and every point on the wheel. So in this picture, every point on the rim, okay, is moving at the same speed as the center of mass. Okay, so remember the center of mass had speed r omega. Okay, so the center of mass has speed r omega. There's the center of mass. The door handle has that speed. You in the car has that speed, and every point on the rim has that speed. All right. So there's two different velocities associated with points on the wheel. All right. So if I look at this point right there, okay, on the wheel, that one right there. This point is doing two things. It's headed to the right with speed r omega, same speed as the center of mass, because it's attached to the car. Car's headed to the right. And, okay, that point is also rotating. Okay. Now the door handle is not rotating. Okay. So that's the difference between that point on the wheel up here and the door handle. Okay. So the door handle is not rotating. Okay. That point is rotating. So we can think of rolling, and we're going to treat rolling as a linear combination of two motions. Okay? So we can think of rolling as pure rotation about the center of mass. That was that picture. Which was that picture. Okay, pure rotation about the center of mass. Okay, so rolling can be treated as a combination of pure rotation about the center of mass. That's that picture. Plus pure translation of the center of mass. Now, translate means to move to point in a straight line. Okay, so if I move from that point, to that point, okay, in a straight line, that means I'm going to I translate. Okay, rotate means obviously to move around in a circle. Okay, so we can treat rolling as a pure combination, or as a linear combination of pure rotation of the center of mass. So here's what the wheel is doing. So this was motion on the top, number one. So it's purely rotating about the center of mass. So that was the first picture we had way up there. Okay, center mass isn't moving. So here's the wheel you're holding in your hand, rotating about that point. Okay, but the wheel is also doing what the door handle is doing. Okay, that was the door handle. Okay, so the door handle is moving to the right. Every point on the wheel is translating to the right with the same speed as every other part of the wheel. Okay, the mirror, okay, the hubcap, okay, your backpack. So here I have a linear combination of pure rotation about the center of mass plus pure translation of the center of mass. Right? So remember, the center of mass from this picture had linear speed r omega. So every point on the wheel, that point, that point, that point, that point, has the exact same speed as the center of mass, which is the axle, because it's moving down the road with the car just like the door handle. So if I add these two motions together, pure rotation about the center of mass plus pure translation of the center of mass, okay, I add these velocities as vectors. That vector plus that vector gives me this long vector. So this is the same as the center mass speed r omega. That's r omega. I get 2r omega. Okay. If I add up the velocities of what's happening at the axle, that one's 0 plus this due to pure translation, v center of mass is r omega. Okay. That's what we had here. V center of mass was r omega. Okay. So if I add up 0 plus that vector, I get the speed, the velocity center of mass. Okay. Now the bottom is kind of interesting. Okay, the contact point. Okay, so the contact point, okay, where the tire touches the ground, is headed to the left with velocity r omega because it's rotating. But the bottom of the wheel is also headed to the right, okay, with the same speed as the door handle and the rest of the car. So the bottom of the wheel, where it touches the road, is headed to the left. Okay, I hope I said that correctly. Headed to the left with velocity r omega due to rotation, and it has a velocity to the right of r omega due to translating. So those two arrows cancel out, and they give you 0. So that says the velocity at the bottom of the wheel is 0. So the bottom of the wheel has no relative motion with respect to the ground. All right. So a couple interesting things from this picture. Okay. This says that the top of the wheel is moving with twice the speed as the center of the wheel. Okay. And the bottom of the wheel, okay, that contact point is not moving with respect to the ground. All right. So let me give you a better idea of what's happening here. Okay. So here's you in the car. Okay. So the car is going down the road at 50 miles an hour. Okay. The door handle is going down the road at 50 miles an hour. Here's someone else, okay, watching the car go down the road. All right. Okay, so every point on the car is moving to the right. It's translating with a speed or velocity of 50 miles per hour. All right. Looking at this picture and that picture. Okay. All right. So let's see. So the car's headed to the right at 50 miles per hour. Door handle's moving to the right at 50 miles per hour. Okay. The center, the axle, is moving to the right at 50 miles an hour. Okay. We saw that the top of the wheel, okay, this is the wheel, top of the wheel, has linear speed 2 times the center of mass. Okay. So the top of the wheel is doing 2 things. It's heading to the right, okay, due to rotation, and headed to the right due to translation. So those 2 arrows, there's one there, there's one there, okay? Those added up to 2 times the speed of the center of mass. So the car's headed to right at 50 miles an hour, door handles to the right is headed to the right at 50 miles per hour, but the top of the wheel is headed to the right with a velocity of 100 miles per hour, okay? So different points of the wheel have different velocities and hence different speeds because they're doing different things. The center mass of the wheel is only moving to the right. Okay, top of the wheel is headed to the right, just like the center, but it's also rotating. That's why you actually add up, and you can put these if you want. You don't have to, because 100's not a vector. But okay, think of adding those 2 arrows as vectors. Okay, now if I look at the bottom of the wheel, we showed that the bottom of the wheel, remember, wheel's rotating like that, has a velocity to the left of 50 miles an hour due to rotation, and has a velocity of 50 miles per hour to the right because this part of the wheel is moving with the same speed as the door handle. It's moving to the right at 50 miles per hour. These 2 velocities cancel out, and that says the bottom of the wheel has no relative motion with respect to the ground. So I call that point Q. Okay, so point Q is a stationary point of contact. There's no relative motion between the wheel and that point Q, okay? There's no relative motion between the wheel at that point Q and the ground. So here I have a bike wheel. Okay, so I could ask, well, how is all this stuff, these arrows up here, demonstrated in this picture? Okay, well, if I look at the spokes, okay, I look at the middle of the wheel, okay, we said the middle of the wheel has speed, center of mass. Top of the wheel has speed to the center of mass. Okay, so if this person on the bike, their speedometer reads 10 miles per hour, okay, the speedometer on the bike reads 10 miles an hour, okay, the seat of the bike is going at 10 miles an hour to the right, okay, if their lunch is in their backpack, that lunch is moving to the right at 10 miles per hour. This little axle right there, okay, is moving to the right, that's the center of mass at 10 miles per hour, but the top of the wheel is moving at 20 miles per hour, because what is the top of the wheel doing that the bike seat is not doing? Top of the wheel is also rotating. Okay, so 2 different points of the wheel have different velocities, and the bottom of the wheel we said had a relative velocity of 0 with respect to the ground. So if I look at the spokes, okay, the spokes here are more in focus than up here. So these spokes are out of focus. It actually shows they're moving much faster than the lower spokes over here. Okay, now if you look at the bottom, that's much more in focus. Okay, because this chunk of the wheel is headed to the left due to rotation, headed to the right with the same speed as same speed due to translation. Those two velocities cancel out, and so the bottom of the wheel has no motion with respect to the ground. So that's why that's more in focus than the top of the wheel. Okay, so again, if I look at the wheel, all right, imagine if I had a chunk of mud, okay, stuck to the wheel at different places. So, so here's the person on the bike, all right. So I didn't draw the metal attaching the axle to the seat, okay. So here's the person on the bike. So let's say the bike's moving to the right at 10 miles an hour. Okay, the person's moving to the right at 10 miles an hour. The seat is moving to the right 10 miles per hour. And this is the picture I just had above. So the center of mass of the wheel moving to the right at 10 miles per hour. The velocity at the top of the wheel, okay, is 2 times the velocity of the center of mass. So the top of the wheel is moving at 20 miles per hour, okay. So if I had a chunk of mud, let's say was somehow at the axle, okay, there's my chunk of mud, okay, at the center of mass, and that mud came loose, okay, what would be its path? Well, right before it came loose, it was headed to the right. So it looks like a projectile. Okay, so it would just be a parabolic path. It'd be a projectile. Whoops, and then hit the ground right there. Okay. Now, what if I had that same piece of mud up at the top? Okay, and it came loose at that instant. Well, it's headed to the right with a speed of 20 miles per hour, okay, horizontally, so it now looks like a projectile. Okay, it comes off, parabolic trajectory, hits the ground right there. Okay, what if that same piece of mud was over here? Okay, what is that piece of mud doing? Well, it has 2 motions, okay, from the previous pages above. It's headed to the right with the same speed of the center, same speed as the center of mass, okay, because remember, the bicycle seat's headed to the right, okay, the axle's headed to the right, that chunk of tire is headed to the right, okay, due to pure translation, right, at 10 miles per hour, but it's also headed upward because the wheel is rotation. The wheel is rotating. Okay, so if I add these 2 velocities, okay, I have a box. Add those 2 velocities. All right. So here I have a box. So I have a leg here. Okay, and I have a leg there. So here's my box. Okay, and I want to find out what is that diagonal. All right, what is that diagonal C? So I have a box. So Pythagorean theorem says that side squared plus that side squared, a squared plus a squared is c squared. So a squared plus a squared is 2a squared. Okay, take the square root of both sides. That says c is a times the square root of 2. And on the calculator, square root of 2 is about 1.41. Right? So if this is 10, okay, and that's 10, right, 10 miles per hour, 10 miles per hour, my picture up there, then c, okay, then this green one there, okay, that would be v center of mass is 10 miles per hour times the square root of 2, and that's 14.1 if I do that in a calculator. So that says when this chunk of mud comes loose here, it heads off in the direction of that green arrow, okay, with a speed of 14.1 meters per second, or not meters per second, that'd be miles per hour. Get rid of that, like that, miles per hour. Okay, and then it would look like a projectile. It would follow this blue path, okay, and eventually hit the ground somewhere over there. All right. Now, okay, what if that chunk of mud, okay, we did it at all different places. Let's say it came off right there, okay, came off at point D, okay. Well, this point of the wheel, okay, the mud is attached to the wheel at that instant, okay. So right before it comes loose, it's headed to the right with a speed of 10 miles an hour because every point on the wheel and the bike is moving to the right at 10 miles per hour, okay, and it's headed in that direction, okay, due to rotation, right? So the velocity, okay, would be 10 miles per hour tangent to the wheel or tangent to the radius, all right? So to find the velocity with which the mud comes off the wheel, I have to add those 2 vectors. So I'm using the parallelogram method, tail to tail. So this arrow here, okay, remember how I did that? So a parallelogram method, my body diagonal would be the velocity of the mud, and the magnitude of that arrow would be the speed with which the mud comes off the wheel. So that's a much bigger arrow than the green one above, okay? If I look at the angle, once the mud comes loose, it follows that path okay, and hits you right there in the back, okay? So on a muddy day, how can you avoid getting your shirt dirty, okay, when you're riding your mountain bike, okay? Easiest way is borrow your lab partner's shirt, all right? Okay. Another way what people do is they go like this, and then they go like that, okay, and they put a fender. Okay, they put a fender on the bike. So what does the fender do? Let's see. What the fender does is when that chunk of mud becomes loose, okay, instead of hitting you in the back, it's just bounced up. Oops, that's bad. It bounces up, hits the fender, and heads down. It doesn't hit you in the back, okay? So, but most people don't want to put fenders on their mountain bikes because even the squirrels would come out and laugh at you. So, like I said, they just borrow someone else's shirt and don't worry about it getting dirty. Okay. Now, if I look at the bottom, okay, so what's happening at the bottom? So let's say here's my piece of mud, okay, and this piece of mud comes loose right there. What is that piece of mud doing? Well, it's headed to the right with a velocity of 10 miles an hour due to translation, because every part of the bike is moving to the right at 10 miles per hour, just like the person and the cart and the bike seat. But it's also headed to the left at 10 miles per hour because this point is rotating. So those two velocities cancel out, and that's why we said that's a stationary point of contact. So when the mud comes loose, that mud would just stay right there on the ground, and the wheel would just keep on rolling past, right? So that's why we said in the earlier chapters, we had the car coming at us, okay, and we said that, well, we knew the acceleration was toward the center, and we said, okay, well, there had to be some force that pointed toward the center, and we said it's the friction force. And we asked, was it kinetic or was it static? And we said a couple reasons that it was static, okay? One of them is, we know it's not kinetic because there'd be skid marks, all right? But it's static friction is because when any part of the tire touches the ground, okay, there's no relative motion, there's no skidding. So when this part of the tire up there is about to hit the ground, okay, it meets the ground, and then it's no longer touching. So it's no different than if you took the wheel, okay, placed it on the ground and picked it back up. Okay, these 2 points, that part of the wheel, okay, is going to meet that part of the ground, okay, when the tire gets there. They touch and they no longer touch. There's no left and right shifting. There's no slipping. There's no skidding. So that's why I said back in that chapter that we'll have to wait till the rotation chapter to argue. That's why it was static friction.